idea behind the pedagogical demo is that CSIE brings in education experts to talk about really innovative ways that they're really innovative teaching methods that are being used in the classroom. So I'm really excited to introduce both Professor Risa Kelly and Professor Barry Fishman. Risa Kelly is from San Jose State University. She's an associate professor, and her research is focused on how undergraduates understand animations and molecular visualizations, and also in the development of these tools. And then Barry Fishman is creator of Gradecraft and a professor of learning technology at the School of Information and School of Education. So he's going to talk to us about gameful classrooms and his program Gradecraft. So what we're going to do is just have them speak for 25 to 30 minutes, one after another, and then open it up to discussion. So just save your questions till the very end. And so Risa.
All right. So when I was putting together this talk, I decided to put just a hodgepodge of things that I try when I'm teaching. And some of these are based on the research that I do, and some are not. So I'll kind of give you that as we go. So my goal is to share visualization ideas with you and consider how they might work for you and how my research has influenced my practice. So to set the stage, this is how I would actually approach, actually in my general chemistry course this semester, I started out by asking, after I introduced the syllabus for the course, I asked my students, okay, so what do you think about when you think about the atomic level? Specifically, if I were to ask you to draw a neutral lithium atom, I didn't want to go with hydrogen or helium, I wanted to give a little bit more than that. So I thought, okay, lithium's the perfect element, right? What would that look like? What subatomic parts would you include? What would you draw? And then I give them time to draw it. And so then I'll kind of walk out, and this is a big lecture auditorium. And what always kind of shocks me is that initially I'll see some students who, they won't draw anything. They'll sit there and they just look like they're gonna wait for the answer. And so I started to think, like, I'm like, well, you know, you have to do this. And they're like, still wasn't making them do anything. So I said, well, I'm gonna have you turn this in for credit. And actually, I didn't say for credit, I just said, I'm going to have you turn this in. So then I'm like recognizing that I didn't say that I was going to grade it, I just said I was going to have them turn it in. So I gather like 200 and some drawings, and then what I do is I collect them. And too bad, it's hard to see this one. But basically, I actually showed this slide to my students. I said, these were some of the representations that you came up with for drawing a neutral lithium atom. And what I want you to talk about right now is, what are the similarities between these models and what are the differences that you see? And how would you decide whether or not that model is supported or refuted by evidence that you're aware of? Or do you think these drawings, and you can be honest, those of you who made the drawings, did you draw this just from what you've memorized and what you've learned in the past from when you took chemistry when you were in high school or when you took chemistry before? And so it was interesting. If you look at this, there's quite a bit of similarity in the pictures, but then there's also these subtle differences. Some use color, and we talked about the use of color in terms of making your drawings a bit more exciting, a bit easier to see some things. But what's kind of interesting is how the scale of the electron compared to the scale of the atom, or the protons and the neutrons, or in this case, no real neutrons in the pictures. And how they're, actually a few have neutrons, but trying to get across, well, so some of you have neutrons, some of you don't. Some of you, you've got these rings in there. What does that mean? So we spent a bit of time discussing the features, and the scale issue of how much smaller electrons are than the protons and the neutrons doesn't often come up. But then, what the meaning behind the rings are, that's another kind of topic for conversation. But so then I'll have them look at, okay, so these are some of the actual models that I've just pulled from doing a Google search, and this is what we came up with. So how are these similar to what you do? How are they different? Which one do you think is more accurate in its representation? How would you know that? And so it's starting to plant this idea that they have prior knowledge going into the course, and how are they going to modify that understanding based on some of the things we're learning in the class? What evidence are they going to use to support or refute the pictures in their mind? And how would they defend that to somebody else? So I like to start with this because it gets them, it sort of a way to keep it kind of low anxiety, because they're just making their drawings and no one knows which drawings end up on there because there's no names, and then they get a chance to discuss it, and it starts to build this idea that they can draw pictures, because some of them don't believe that they can. So then I kind of close it with, could you gather, select, or use data as evidence to support your atom model? What counts as evidence? What counts as your opinion? And how would you link this to evidence? And some of them start to talk a bit about the historical research that was done in terms of the Rutherford experiment and how J.J. Thomson contributed. Some of them go there, some of them don't. They just know that they memorized it in high school, and that's good for them to be aware of as well. So what convinces them? So that's how I started. Now, this part is a little bit more of how I would connect this to some of the research that I've done in the past, which is looking at how to use visualizations. And to give you some perspective, when I started as a high school chemistry teacher. And one time I was evaluated, well, many times, but one time that I remember was the curriculum specialist. He talked to me after this lesson that I did, and I was looking at periodicity and activity series of metals, and wasn't really at that time, this was in like 96, wasn't a lot of visualizations that were out on the market at this time. There was one by like Data Logger. We had some Vernier software that we had like probes and they collected data, but nothing real spectacular in terms of animations that I could use in my class. But he, after this lesson, he said to me, your lesson was good, I have no complaints, I just noticed you don't use a lot of technology in your teaching. So I'm wondering, what you could do to ramp that up a bit, so we, because that's one of the initiatives of the school at the time. So, I was kind of like, okay, really? That's what you're going to critique that about my lesson? It was great, but so I was kind of like, but at the same time, I was working on my master's project, and I was trying to get a master's in science education, and my thesis advisor was asking me to come up with a project, and I was, had no idea. And she said, well, here at Northern Iowa, this was Amy Phelps and Michael Sanger, we started using these macromedia tools, or simple animations, and we're having some pretty good success with our college students really responding to the information that's presented in these really simple animations. So maybe you could try this with your high school students. So that's where I started to consider how I would introduce these animations, and when I first saw them, it was a chance to kind of see an animated, concrete model of how we might discuss the movement of atoms within a context. So I wanted to connect this to some laboratory experiments, and their animations were of these things. So the question became, all right, how do I introduce this to my students? So first thing that I could do is show them a demonstration. So here's a demonstration of the crushing can demonstration, where you take a little bit of water, place it into the bottom of, or into a can. You heat the water, and again, the gas in the can is leaving, but you're replacing it with water vapor, and now you're putting it into the water bath, and the pressure differences causes the can to collapse. I wouldn't tell my students this, by the way. I would ask them, okay, observe what you see, and now here's an animation. I'm only showing you a still image representation of the animation, but in this particular study, we had two groups of students, and the demo was done for both of the students. So in both of these classes, the other teacher showed them the same crushing can demonstration that I showed my students. And then we both asked our students to predict what would happen after the demonstration, and asked the students, what would you picture happening, why? And then the treatment group viewed the animation. But the other group did not. They just went through, like the teacher provided the explanation and worked with the students to identify the key components of what was happening. And then administered a post-test. Now, this was my first time doing research, and the study was very flawed, but it was a good first step in doing research. And what this taught me was that when you're connecting to teaching, the students did have the opportunity to study animations, or they didn't have the opportunity. The teacher was the one who was kind of going through and telling the students, this is what I see, these are the important parts of the animation. The students didn't have the opportunity to do that. And what I noticed is that this was something that the students really needed time to do. And so I ended up thinking, okay, based on this evidence and recognizing that they are picking up on a few more details. That's the one aspect where when I looked at the two groups in terms of their responses to questions, the students who had seen the animation and had representations to refer to were much more detailed in their drawings. So that was a positive benefit, but I felt like, again, they were really stifled by the whole teaching setting. So now how do we bring this around so that the students are in control of their learning from this animation? So I ended up taking that demonstration and making it a station of multiple gas law stations that the students could go through. And then after they completed they did the activity themselves, they were asked to explain how they would account for the result that they had. And then after they first had done this explanation on their own accord, then they were told, okay, we had one computer in the room. So I'm like, okay, you're going to go over to the computer and you're going to check out this animation, and then I want you to modify your understanding if you feel like it's necessary, if you gain anything from watching that animation. And in doing it that way, and I didn't study this, I just followed it up, because I'd done my master's and I'm done with it, right? but I implemented that, and I felt like the students, the understanding that they took away from it was a bit better. So that's where I've decided that we can start to go in our animations, we can go a little bit further in, again, presenting these opportunities to our students, giving them the chance to critique what they see. So another tool that I use is simulations. Now this is one developed by Tom Greenbow. He was at Iowa State, and now I think he's at Oregon State. And it's a really simplistic model representing activity series of metals, where you're given a series of solutions and some metal pieces, and they're simply asked to, what would happen if you place these metal pieces into their respective solutions? What does that tell you? And they're given some controls to play with. And so here's a situation where the metals are raised above the solution. You're going to test this magnesium metal in these 4 different solutions. Now, what's going to happen? So here's the outcome. This is sort of the during and then the after. These were the metals that reacted. And so now, instead of just introducing the students to the activity series of metals, what I try to get them to do is like, okay, so what does this tell us about this particular piece of metal within these solutions? What do we know is happening to magnesium? So if we're just starting to talk about redox, we're starting to identify, all right, so magnesium, neutral metal, now you're placing it in these solutions. What's happening to the magnesium? What's happening to these metals that are in solution? Where are they ending up? Are they the same or different? Once they were ions floating around the solution and now they end up on the surface of this metal, is it still an ion that ends up on the surface of that metal, or has it changed? What's happening? So starting to get them to think about what's going on in a redox reaction and how the ion form is different from the neutral form, and how we get some metals that plate onto other metals and some that don't. So then you can go through and place the copper pieces into the solutions, and again, you can look at the fact that, well, copper, only one of them, it only reacted with one of the solutions. So what does that tell us about the activity or reactivity of the copper in this particular situation with these other solutions? So that's another approach where you can bring in kind of canned experimental results that it's based on what would really happen, but it's not the actual experiment. It's a simulation of the reaction event. And you can start to get the students to think about how they would construct their own activity series of metals for these particular metals. And that's what I had my students do. But then ultimately I want them to connect back to, okay, what does this actually look like? So it's great that we have this cartoon representation, but what would you actually see in the laboratory setting? So here's a still image showing progressively different times of what this reaction looks like. And then asking them, would the reverse reaction occur? And how can you test this? Give it a try. So they're introduced to the macroscopic representation, and then of course they can see actual animations. So this is where I've been going in terms of my research most recently, is to show students some experimental evidence in terms of video kind of demonstrations of experiments. So not just a still image, but showing them an actual video. And then saying, all right, here's a couple of animations. I don't know which is right, but I want you to try to figure out which one is the best. What evidence would you key into that would support this animation as the animation that you think is representative of what's happening? What aspects do you think aren't supported by what you see experimentally? I want you to decide that, and you're the winner here. You get to make that decision. So let's see if I can get this to play. This is the Roy Tasker animation. There's a narration that goes with it. So I'm just going to pause it for a second and point out a few of the aspects or features of Roy's work. Roy, at this time, these animations were, I think, constructed in the early 90s. And at that time, rendering these animations was quite an issue. So they had to go in really close up, so they didn't have as many things to animate. As a result, you get this, the close-up perspective that you get is somewhat confusing to students, and they're oftentimes, when they first see this animation, they're a bit put off by it. Like, there's just too much going on there. But they're reluctant to ever replay this animation because, again, it's only just started, and it goes through kind of repetitions. Different areas within the animation are highlighted, and the student kind of keys into the fact that, all right, you have oxidation happening at the same time as you have reduction. And so did you notice that the copper ion's leaving at the same time that the silver ion is being reduced? How do you see this? So it points this out to the students and kind of scaffolds it, but it's still a really complex reaction or animation for them to make sense of. And so they're a little bit put off by this, but when I do metacognitive monitoring exercises where they have the students list what they see happening in the animation, they pick up on all of the animation features. It's not that they don't see them. They do pick up on all of those features. But then when they're asked to modify what they initially started with in terms of their picturing of the reaction at the atomic level, they don't always choose to take every single feature that they saw and incorporate that into their pictures. They're choosy about what they pick, and a lot of it depends on a bit of the way that they think about the chemistry in terms of kind of the complexity that they already have, how well they're able to draw to different areas and accept a model and apply it. It's a tricky area, but it's fun. So that animation was contrasted with this animation that I intentionally designed to make it wrong. So this one's a really quick one, and it doesn't have narration, so you can just watch. It starts with a macroscopic representation, and you zoom in. So here we're looking at kind of the physical aspect of how this reaction would take place. And it's actually, again, it's wrong. But there are aspects of it that overlap and actually the two animations support the idea that copper is a lattice arrangement of atoms. It also supports the idea that the silver ions end up kind of plated onto the copper surface. So they have things that reinforce each other, but then they also have places where they differ. And so what I wanted to see is what students would do with the differences. How would they respond to the conflict? And again, what I'm finding is that students' background in terms of like, you have those students that they try to connect to every single thing that they're learning in chemistry. Do you know those students that's like you're teaching, if you look at this redox reaction, I mean, they will tell you about Lewis dot structures and electronegativity. They go through like everything, they try to make sense of it all, like, oh, it's gotta be this too. Those students actually do quite well with the complex animation. And they're already trying to draw those connections, and so when they see a complex animation, it's not, I think, out of their realm of ability to bring these pieces together and connect it to what they were thinking. So it's not as much of a leap. But if a student had really simplistic understanding in the sense that it was even difficult for them to have the academic language to describe the reaction environment, like they might talk about the atoms, they stick together. A number of students think that every single atom that's in solution must just layer onto the solution, and that's what has to be the muck that ends up on the copper surface. They have a harder time making sense of the animations and reasoning how they could, how one could be right over the other. And a lot of them will go with a more simplistic model And I think in part it's because it's easier for them to, one, explain, but it also it's reinforcing the way that we teach, which is to start with equations. And with equations, when we teach equations, you'll notice that there's a right and a wrong answer. So if you're graded, you can get the equation right or you can get it wrong. And so they've gotten affirmation about the understanding of those equations. So now when they see these two animations, they're like, well, this one fits with what is going on in this balanced equation exactly. So I think it must be this one. And so the reasoning is a little bit, so they're not quite as able to pick up on or apply the nuances, but they do, interestingly, it's not so cut and dry, because when you look at the pictures that they construct, they'll incorporate a lot of the features of the Roy-Tasker animation within their drawings. So it's not like this, they only went with one. They do kind of pick from both to revise their understanding. And so that's been, and we're still plowing our way. It's a qualitative study, and so these were 2.5-hour interviews that I did last fall. Just got the transcripts completed by May, and have been analyzing the data for quite a while now, and hoping to write up some of the findings soon, but we're still kind of in that process of figuring out what it all means. But the idea is to introduce this as something that you apply to your teaching. Like, could you see where you could present students with a couple of different cases and then get them to discuss, okay, how do you support this model? How do you refute it? What do you do to make that decision without an instructor telling you you're right or you're wrong? That's what I like to try to do within my teaching, is try to get them to not see me as the expert in the room, which half the time I never feel like I'm the expert in the room. I have that like imposter syndrome, right? But so I like to have the students start to have the conversation, so we can have more discussions about how to approach or how to think about it, and just creates a bit more comfort. This is one final teaching strategy that I've also implemented, and this one is using click and drag tools. So this is just with a simple titration reaction, and you're all probably very familiar with this, but typically you see the common problem of, okay, here's a known concentration of your sodium hydroxide or whatever you're titrating with, and you want to find out the concentration of this acetic acid solution. So how would you solve the problem? How would you figure out what the concentration of the acetic acid solution is? Well, that's fine. It gets them working on that problem, but what are they actually picturing in terms of what's happening at the atomic level? So I actually went through and had a programmer work with me to create some click and drag tools. And the importance of this click and drag model is that it includes proper species that you could select, but it also has some red herrings, all right? So here are some not so traditional species that you could choose, and the idea is to let the student kind of explore their understanding. What do you think a sodium hydroxide solution would look like? And how would you know which is the best model to choose? So inevitably, I've given students some these are actual pictures that students have constructed using the tool, and then I'll present these to the students and I'll say, well, I had a number of students come up with these pictures. So how do we decide which one's a good representation? Are they all the best representation possible, or are there ways to even improve on the one that you think is the best representation? So starting to kind of open up with a discussion of even how we represent these aqueous solutions. So here's a strong base. What do we know? What physical evidence do we have to tell us what that solution looks like at this level? So that's how I make use of that tool. This is just looking at the acetic acid solution. And these are also some pictures that students construct, and trying to get them to again, make sense of what these students have drawn. How would you know which is the best model and why? And then through the tool, they can look at, you're adding your sodium hydroxide to the solution at this point. So what you would see, there's a little bit of an animation where a few drops are added, and it's like pink, but then it goes back to clear. So recognizing that the equivalence point has not been reached, what does this look like in the solution? What does it look like when you reach your equivalence point? How does that, how would that look in the solution? And then if you overshoot it, what does that look like? And then providing them with some representations that other students have done to see how they have represented it, and discussing kind of, again, what are the attributes that you are in favor of? What are some things you would change about these? What are some complications? Where are places where you might not be sure of what's going on? How do you deal with that? So that's how I use that. And the next part I was going to go into is more my research, but I'm wondering time-wise, is that, two parts?
About 5 more minutes.
5 more minutes? Well, okay, so to give you, so this will be a really quick drive-by. When it comes to designing animations, when I first started as a graduate student, I worked with Loretta Jones, and she had Roy Tasker, who created the animations that went with her textbook. And I saw Roy Tasker present at a visualization conference, and what struck me most was that when he presented these gorgeous animations, that this room of chemistry professors just had a field day with critiquing them, like, oh, why didn't you change this, or why do you have sound in there, and this is horrible, and and you're looking at what seemingly is a really good animation, but these experts are critiquing them. And that's what you should do. You should critique the animations and recognize the flaws. But what I've noticed again is that when we're teaching with animations, we tend to use them as, here's the explanation. Make sure that you understand all of the features of the animation and memorize it. It's no different than really a lecture. And there might be some test questions that people would ask with their animations, but we weren't really getting students in a mode where they're actually thinking about the information that was presented to them. So when I first started, I was trying to make all of these people happy. Like, I recognized that when it comes to designing animations, we really need to find out what instructors are expecting to see. And if I had more of a sense of what instructors wanted to see in this animation, then I'd have a better sense for how to design the animation. So I actually did a study where I interviewed professors at San Jose State, various stages, various disciplines of expertise, and asked them, all right, if you were teaching a Gen Chem audience and you were hoping that for the best possible explanation that these students would come up with, could you draw or construct for me using these click and drag tools what that would look like for a few different reaction settings? And so what I found, I'm going to zoom past it, so I used the click and drag to look at that, is that these are 3 instructors. I actually interviewed 9, but these 3 all taught Gen Chem or were immersed in teaching Gen Chem at the moment. And these were how they, I guess, came to terms with how their students should recognize distilled water. So Y and Z are pretty similar in terms of how they represented the distilled water. But Instructor X was much more detailed. He actually had designed animations himself, and so was very into recognizing every little detail that he could possibly come up with. And this is 2-dimensional, so it's not even all that it could go to another dimension of complexity. So I was recognizing, seeing a distinct range in you got instructors that are just trying to give you a sense of the water molecules that are there, but again, liquid state, it's probably water molecules are much closer together. So Instructor X is probably more accurate in terms of his depiction, but Instructor Y and Z were very adamant that students could handle too many water molecules. They wanted to keep it simple enough for them to be able to kind of have a sense of what was going on, but not get too caught up into so many details that it turned the students away. So this is how they represented solid sodium chloride. Just the differences between those. Here's an aqueous sodium chloride, how they would represent those. And what I ended up doing was putting these together to design my animations. So if you focus right now on the solid sodium chloride and how that might look if you were to test it for conductivity, we know it doesn't conduct, but how would you represent that? How would you depict that in an animation? I wanted to be true to the different levels of complexity that I was seeing. So in the first picture, I start off with more of just a 2-dimensional kind of separation of the ions, and then it morphs into more of a 3-dimensional look, and then you get kind of the ending where the electrode is present, and it's a bit more true to the instructor that had the complex representation. And in these pictures down here, you're seeing, I actually played with 3 different layers of complexity. This first one is the most complex. This middle one is graying out the solvent water molecules to only color the water molecules surrounding the ions. So you can see kind of the drunken walk that the ions do as they're trying to get over to the electrode. And then here I tried to go with more of, let's kind of reduce the number of water molecules in the solvent to make it easier to follow what it might be like as these ions are migrating over to the electrode. So I ended up studying this and looked at how students, like what they pictured first, and then they would watch the animation and describe what they would see. And this is just showing that part of it. And I did the same thing with the aqueous sodium chloride solution and looked at how students would respond to the animations. So that was kind of the tool. This is where it all first started in terms of my research and trying to develop animations that were pleasing to the different levels of instruction that, or I guess the features that instructors wanted to see represented in the tool. So I was trying to make everybody happy, and of course, when you try to make everybody happy, you make no one happy. So it was informative, and I think the tools are useful, but the other limitation that you don't see is that animation artists sometimes can't create the complexity that you want to see because you're limited by their design abilities and what the design tools allow them to create. And so, so that's where we struggled a little bit in trying to convey kind of this motion of the ion going toward the electrode and how it's not just like a straight line and it's a bit chaotic and then the ion bumps into water molecules and that affects its path. I was trying to get that represented, and it's like not even a second. And so, but that's when I started to realize that maybe it's not so bad to not have every single detail portrayed. What if you leave some room for the student to then say, well, now you see this animation, is this the best way to represent it? So again, to start to bring them into more of that critique mode. And that's kind of where I've gone, is to bring students in and helping them to critique. These are just some tutorials where I started to bring a cartoon person into the helping with the explanation, and I was really focused on knitting together macroscopic, submicroscopic, and symbolic levels of chemistry together, and the cartoon person was essential in helping to knit those pieces together. So just how that was done. This is a different cartoon, Dr. Energy. My students came up with that name because energy, and yeah, so anyway. And they came up with the little lab background. So I typically start with a question and ask students to ponder, all right, what happens when you mix two solutions together? Sometimes you get a precipitate, but sometimes you don't. Why is that? How can we account for that? So always starting out with an exploration, a kind of a question to get them to think about the problem, and then how would you maybe represent this in terms of the atomic level? And that's where we went with those, is to try to do that and to get them to see animations and then have the tutor kind of go in and help students make sense of it and address some of their misconceptions up front, and then have an application process where you went back and said, all right, now we're going to take this and look at what we actually get. How can we make sense of that information that you just learned about there? So that's what the tool does. So that's just a little bit. These are some results, but they're decent. That's just some ways that I infuse technology into my lessons. And the thing is that I think there's a lot of opportunities for ways that we can bring these tools into our classroom and invite our students into the conversation about the concepts, which is what I like to try to do. But there's also, there's the parts where you've got to be ready for, I'm in Silicon Valley, which you would expect that we would have like primo equipment, but we don't. And so when you go into the lecture setting,